Thank you very much. And I also want to thank the organizers for organizing this amazing workshop and inviting me to this beautiful city. So today I want to talk about modular graph forms. Um, I don't want to put much time on where they come from, but just to give you a background, these things come from the amplitude of closed strings at world sheet one loop. So at one loop, the world sheet becomes a torus, and we have some closed strings as external states. And if we take them to be asymptotic states, then they become vertex operators on some punctures on the torus. So in order to get the amplitude, the path integral gives us an integral over the moduli space of n puncture torus, which can be split into an integral over the moduli space of a simple torus, I denote it by m, and then an integral over the configuration space of the punctures over the torus at, well, let's say fixed tau. Tau is the modulus of the torus. Um, so the low energy expansion of this object here gives us what is called modular graph functions or modular graph forms. So you can see them as some kind of Feynman diagrams, but on the torus. By the way, I write tau as tau1 plus I tau2. Tau1 and tau2 are the real and imaginary parts of tau. So, okay, how can we write them? So we have to draw some diagrams, and then we have to assign some kind of Feynman rules to write these things. So, for example, uh, whenever we have an edge, we should decorate it by two numbers, which are the weights, let's say A and B. And for each edge, assign this function, tau2 over pi. Um, so this P here, actually this lambda here is a lattice. And this prime means exclude 0 and 0 from this lattice. So this is actually a lattice sum. And to, okay, let me. And we actually, most of the times, write it as m tau plus n, where m and n are integers. Okay, so these are the edges, these are the building blocks, and whenever you want to write a diagram, you want to draw a diagram, make sure that the only thing that you have is vertices and loops and meshes, and no other thing. Like this is allowed, something like this. Something like this. So something like this gives you 0, bubbles gives you 0. So all these diagrams are written like this. And in the end, what you have to do is to impose momentum conservation. So see this as some kind of discrete momentum, just that things like this become something like propagators, Feynman propagators. These are not physical momentums or anything like this. So seeing these things as momentums at each vertex, we have some kind of momentum conservation, put some delta function like this, where something like this means the sum of m's must be 0, and sum of n's must be 0. Okay, so simple rules. Then you have some lattice sum, which is your modular graph functions. And so since they are modular forms, they have holomorphic and anti-holomorphic weights. And the holomorphic weights would be sigma ai minus 1, and the anti-holomorphic weight would be sigma bi minus 1 in the form that I wrote there. Okay, if there's no question, let's go to some examples. So the first and simplest examples that we have are when we have just one loop. Yeah? Yes. Yes. You cannot have m and n both 0 at the same time. It's it should be excluded. I always write a prime or something to, yeah. So, okay, let's have 1, 2, all the way up to k. Let me write better. Okay, and let each of them be 1 and 1. Then the function would be tau 2 over pi to the k sum over p with prime 1 over p to the 2k. And this is non-holomorphic Eisenstein series. So non-holomorphic Eisenstein series are modular graph functions. And in this case, they are modular invariant because the weight is written there. So the next simplest example is that I have the same thing, but let the weights be 1 and 0. All of them be 1 and 0. Then what I have again is tau 2 over pi to the k. So now this sum here is a holomorphic Eisenstein series. This is not very important. It's just how I normalize. Many people normalize it in another way. So I can say that non-holomorphic Eisenstein series are also modular graph forms. Sorry? Oh, don't do that. Yeah. Okay. Yeah. In the actual cases that we have, we don't have G2. Yes. Yes. This is non-holomorphic. This is holomorphic. So this is a modular function, and this is a modular form. Okay. Let's go to another one. So this is one loop. This is the easiest. And if I just want to make it a little bit more difficult, I want to see the first two loop that is also 1 and 1, 1 and 1, 1 and 1. So this is E3 plus zeta 3. And the first proof of this was given by Danzagier. And as you can see, this is very non-trivial. You cannot see this immediately from anywhere. So these modular graph forms and functions, they become very, very non-trivial things very, very fast. And what you have to have in mind is that in the end, whatever combination of modular graph forms and functions that we have to integrate them over the modular space of the torus. So if you don't know what they are, and if we, in even the simplest case, we have many non-trivial things, we are in a trouble. So these things in the actually in the recent years also they have been studied a lot by many people, but I don't want to put much time on them. What I want to emphasize I want to focus on today is their integrals. This is something that we don't know much about. So I hope some of you could help me to get a little bit far after this. Okay. Yes. Well, if it's not even there, it's just zero. Yeah. Yeah, yeah. The first case is fine. The second one, if k is odd, then it's zero. Yeah. Good. So, okay, there are so many identities between modular graph forms and functions. And as you can see, this is a two loop. And on the right-hand side, we have right-hand side, we have a one loop and a constant. So we can relate different modular graph forms and functions of different loops together. So one of the things that we can do is to use some kind of derivation. So this is a mass operator. Is it one or two? It's two. And one thing that you can check is that whatever you use it on a modular graph form, it gives you another modular graph form. And whenever you use it multiple times over and over again, or it's better to write the combination of different modular graph forms. It gives you a combination of modular graph forms, but at some point, one of them look like this, a modular graph form times a holomorphic Eisenstein. So now we can use some kind of sieve algorithm that for the other MGFs that we don't know, again, we act by this over and over. Again, we get something like this, and then for the rest, we do that over and over again. And after some point, what we have is just G's, just holomorphic Eisensteins. So after that, we can go back by integrating. So with this algorithm, it seems very possible to write all these MGFs as iterated integrals of holomorphic Eisenstein. It gives you some kind of algorithm to do that. So if I want to go by example, if I don't want to just say some vague things, let's have an example. For example, if pi nabla to the k ek, if I compute this, what I get is gamma 2k over gamma k. So perfect. In order to go from here to here, we have to integrate over and over again to go back to this. So it's good to define some kernels. Let me write two kernels here, kernels of integration. We have a one form, tau1, tau1, which is d tau1, 2 pi I. Oh, by the way, this tau1 is not that tau1. I'm just putting an index here. Sorry for this. And similarly, I define something called omega minus, which uses non-holomorphic anti-holomorphic Eisenstein, the complex conjugate of this. And one thing that I can see is that Yeah, okay, let me also introduce another thing, something that is called beta SV for some reasons that that I'm not gonna explain. This is an integral over omega plus and an integral on omega minus from tau to I infinity with some kind of regularization. So this is an integral that is decorated with holomorphic Eisenstein and anti-holomorphic Eisenstein. And what I can see is that I can write E. Yes. Yes. There's theta 1. This is some rational minus beta SV k minus 1 2k plus 2 zeta 2k minus 1 some rational and tau 2 2k minus 1. No, it's not exactly complex conjugate. It's similar, but yeah, there's a minus sign here, but it's not exactly complex conjugate. Omega minus is not exactly complex conjugate of omega plus. Yeah, I'm not gonna write it. It's too much, but so yeah. So this very simple case, this one loop, you can see that you can write it as the integral of G. And if you go to more complex ones, then it's like iterated integrals of G's. And this is one way to classify all these major graph forms and functions. This was done in 2019 and 20, I think, by Gerken, Kleinschmidt, and Schlatter. Okay. So this is the idea. We have this omega plus and omega minus. We write some iterated integrals of these omega plus and omega minus. We put them together, and then the next thing is that these kind of iterated integrals are not necessarily modular forms. So we have to find their modular completion. And in order to do that, we have to expand the space. We have to go beyond MGFs. And what we get is also the iterated integrals of cusp forms. So these are the things. Make iterated integrals. Find modular completion. Then after doing that, you put some things that you don't want. So somehow throw them out. Somehow find some nice linear combination that mods out all these cusp forms and everything that is unnecessary and you don't want. So this was done mostly by Francis Brown, and you can also, let me give you a source to, yeah, you can also read this paper. For many other cases that all these major completions were found. And then many things that, so we have to expand the space and we have to go beyond major graph forms. So for example, in this sieve algorithm, I told you, no cusp form ever appears. But here, in order to have the modular completion, you have to put some iterated integrals of cusp forms as well. That's a very good question. And what we use for this part is a derivation algebra and some derivation of some free Lie algebra, which this is for the fundamental group of one puncture torus. This is a big story. I don't have enough time to talk about it, but if you want, you can find it more. Mm-hmm. Yeah. Why it can disappear? Well, yeah, that's what I don't want to go to. Uh, Trust me that there are some linear combinations among them that go back to modular graph forms of whatever of all these functions that appear here. So these iterated integrals, for example, this. Yeah. You want to go to, yeah, the space now is bigger. You want to go to the subspace that modular graph forms are there. So for example, look at this. So we had this beta SV, which was made from these iterated integrals, but this is not modular. So in order to make it modular, I have to add something. And sometimes the thing that I add are like cos forms or the iterated integrals and things like this. So the space now is now bigger. I want to go to a subspace of them that have only modular graph forms and functions. Is it okay? Yes, exactly. Yeah, exactly. Okay, so this naturally introduces a notion of depth. Here, depth is a number of iterations that I have in the iterated integrals, or number of these g's or omegas that appear in the calculation. So instead of working with any other classification of modular graph functions, it's much better for me if I want to integrate them to work with depth. And this is not a grading, actually, this is a filtration. So I have to, for example, I can say that some MGF is of depth D and lower, something like this. Okay, if it's good enough, then, so now we have a notion of depth, we have notion of iterated integrals, and if it's good, we can move on to their integrals. We can learn how to integrate them. So let's first of all, let's see what are we integrated over. So what we're integrating over is the fundamental group of SL to Z, and our measure is tau 2 squared. There should be a 2. Yeah, there should be a factor of 2 also here. So this is our measure, and with this measure, the integral over m is pi over 3. But there's a problem, and the problem is that in order to define these modular graph forms and functions, we use Taylor expansion. And this expansion fails when we get near the cusp, where Caspis tau is I infinity. So what we should do actually is we should split this fundamental domain into two parts. I do this by putting a cutoff here at L, tau 2 equals to L. And I have to treat the other part in a different way. I have to integrate MGFs here, but for the rest, I should not use Taylor expansion or anything. I have to integrate directly. And for example, for graviton amplitude in type 2, it was done by Green and Doker in 2019. So now this is what I want to integrate over. This is the part that I want to integrate over. Okay, what methods do we have? How can we do this? So the first method that I want to talk about is to write down the Poincare series of this function, whatever it is. So let's call that function f of tau. It must be a SL2 invariant function that the integral makes sense. So let's write this f of tau as some seed function. This gamma is that acts on tau is an element in SL2Z mod out by Borel subgroup, which is Borel subgroup is just a translation by integers. No, I'm not sure if it's obvious. That, yeah. And if they do have a Poincare sum, I'm not sure if I can write it. Yes, it's one of the techniques. And n is an integer. So what I do if I write it like this is that I'm actually considering S transformations by this definition. So instead of integrating over this using the seed function, I have to integrate the seed function over just a strip. And this is much simpler than this. But now the problem is that if I put a cutoff here, let me draw it here. If I put a cutoff here at L, this goes to a rectangle at L, but I have many annoying circles, infinite number of circles here. So I have to integrate over this region. And these circles, they appear tangent to rational numbers A over C, and the radius is this. So okay, what happens if you do that? So let's assume that I can write f of tau as a zero mode. And so I write the Fourier transformation, Fourier series, Fourier expansion of f tau 2 let's assume I can write it as this, like this. Thank you. Then the integral over the fundamental domain with a cutoff is this, 0 to L, 0 tau 2 d tau 2 minus So if you write it like this, then both integrals are also convergent. Let me. Okay, so it's very good if you know the zero mode of f and also the seed function. And by the way, if a0 is also integrable over the whole fundamental domain, I can write this as 0 to infinity f0. This is exactly what we had here, minus from L to infinity. So this only works if a0 is rapid decay. Otherwise, we cannot write it like this. You have to write it like this. This is the only way that it makes sense. So if it's a rapid decay, and if you put L to infinity, then this is called the Rankine. Well, this is some sort of Rankine-Selberg method. And whenever this is not a rapid decay, for something like this, Danzagier proposed some kind of regularization, which is called the Rankine-Selberg-Zagier method. That's a very good question. I should also write f as, thank you, f0. That's a zero mode of f plus fm. Thank you. Yeah. Okay, so this is one of the methods, but so there are many things to ask for, here. Like I have to have this, and I have to have this, and they should be, yeah. Well, after that, this integral is not that difficult. So the other method that we have is to asking something else. Let's say that I also have a Laplace equation for f with some source that I write as s. If I have a Laplace equation like this, where c is not 0, then I can use Stokes' theorem. Then the integral of f is 1 over c. I have to integrate over the Laplacian of f, and this is a0 minus the integral. So the thing is, now I have to know how to integrate this source. But this is very good if I want to go depth by depth. So if I can somehow write a Laplace equation of an MGF, where the right-hand side involves some MGFs with lower depth, then I can do that by a hierarchy. I go to higher depths and I integrate over everything. Sorry. No. Some C. I don't know. Yeah. It's just some eigenvalue for this Laplace equation. So okay, this is a second technique. Whenever I have something like this, then I can integrate like that, with the condition that I know how to integrate this. This is actually the most useful technique up to now, because if you go by iterated integrals, then you have a very good Cauchy-Riemann equation system for them, and you can somehow find a very good system for their Laplacian. So again, go to this bigger space of these iterated integrals, the modular completion of these iterated integrals, and find a basis in that space that you know this kind of function for them, this kind of equations for them. And then perform the integral, and then from that basis, go back to modular graph forms. This is the best technique we have so far. This is the most we can go. So let me talk about this a little bit more, and let's see what kind of functions do we get if you use this kind of basis, a basis with good Laplacian equation. Okay, so let's go depth by depth. At depth 0, the only thing that we have are constants. So let me write 1. 1, the only modular graph function that we have is the non-holomorphic Eisenstein series. By the way, so the integral of this is pi over 3 minus 1 over L. Sorry? No, I'm. This is the thing that I'm integrating over. Oh, so that's not. That's something that I didn't talk about. So yeah, in the end, if you put all the pieces together, whatever comes out should be independent of L. So for this, there is another symbol that we use. It's like approximation symbol that we throw out all the L dependency. Because we know that in the end, if we put everything together in the correct place, there should be no L. Yeah. But yeah, if you really want to integrate over that part, you should also put. So when you go to depth 2, so you have actually two choices. One of them is that writing something at higher depth in terms of the product of things at lower depths. So here, for example, you can write EM times EK. This is depth 1, and the whole thing is depth 2. You can do more actually. You can also write the derivatives of these things. By the way, this is not modular, but this is. You can write the derivative of these things. So at higher depth, some sort of functions that you can have is the product of lower depth functions. And for some reasons that I'm not going to talk about, we call these things shuffle functions. So you could always have shuffle functions, and you could have some new functions, the functions that you cannot write as shuffles. And here, for example, one thing that is very important is what is called the generalized Eisenstein. By the way, here M, K, all these indices are always integers. I don't work with half integers. They don't appear in modular graph forms and functions. So this generalized Eisenstein is one of these it's kind of one of these MGFs at depth 2, but we have to be careful that this also contains cos forms. And in the end, if you want to write the correct linear combination, no cos form should appear. So this is something that we have to integrate over. And the best way to do this is to use this Laplace equation. There is another one, but since the integral is 0, I'm not going to write it. And at depth 3, we have how many? We have 2 shuffles. it's either 3e or 1e, 1f. And the rest, let me write the sources. So the new functions are defined by their Laplace equations, and the sources are, well, it's either em, ek, el, em, f, kl plus s, yeah, or em, ek, el plus cc. So these are the ones that they have non-vanishing integrals. On the sources. That's actually the idea. That on sources you have shuffle functions that are much easier to integrate than the other ones. And using all these things, using this to integrate the sources and using that to integrate the functions themselves, you can integrate everything up to depth 3. But as soon as you go to depth 4, so the easiest thing that I can write at depth 4 is em, ek, el, es. And at the time, we don't know how to integrate them. So this is the boundary of knowledge that we have so far. I will write something else and then I will explain why we get stuck there. Yeah. So what do we know? So we can use these integrals. We can write the basis, put them back to MGFs, and write everything for the scattering amplitude of string theory. And what is known now is so up to alpha prime to the 6, everything was calculated by Doker and Green in 2019. And there's an ongoing work with Emil Klassen that we are going to alpha prime to the 7. And after that, you need depth 4, and we get stuck. Okay, so since the calculation stops here, let me tell you some general things on what to do next and what general things do we know. No, even at weight 6, you can you go to depth 3. But the good thing about weight 6, which is depth 3, was that there are so many identities that you can go back to many simpler ones. But for alpha prime to the 7th, you actually must go to this. You want examples of MGFs at weight 6? What? Oh, for 4 gravitons. These are for 4 gravitons. So it's related to this is related to the 12 or to the 4th for 4 graviton type 2. Yes, yes. Okay, so let's talk about a very general function f tau again, which has this plus other non-zero Fourier coefficients. And let's say that A0 has a Laurent polynomial. I write it by alpha n. And n is in a finite set of integers. And a rapid decay part. This could be like exponentially fast decaying function. So now I can actually write the integral of this over ml. Where is it? Oh, okay. This is pi over 3 alpha 0 plus alpha 1. Okay, before I talk about this function, let me say that these two are completely L dependent. So in the full amplitude, we don't need them. So I'm not going to talk about these two. This is exponential. This is something like this. And this is just a polynomial on L. What about this thing? Let me write it. And zeta star is the completed zeta function. Yeah, exactly. So this is actually a Rankin-Selberg L function. So these two are trivial. These are just the Fourier coefficients of your function. And the only non-trivial thing is this, which is the residue of Rankin-Selberg L function on the boundary of its critical strip. Yeah. It doesn't matter. Both. Usually both. Yeah, sure. Yeah. Yeah, these MGFs are not convergent over the whole fundamental domain. But you should not integrate them over the fundamental domain. Yeah, that's right. Yeah. So it's true that we cannot go higher in calculations, but the question is at least uh, what type of numbers can you get from this M of f? So that's a question that I would like to know the answer. So these f's more specifically are some iterated integrals of Eisenstein series. So it's good to know the space of all the numbers that come out of the Rankin-Selberg L function of the iterated integrals of Eisenstein series. And so in the cases that we saw, some of the examples, so for example, we have Euler-Mascheroni that comes out of this. We have zeta star x over zeta star prime x over something like this, zeta star prime over zeta star, and log of pi, many different things come out. So, and the other question is that do all of them appear in string amplitude or not? For example, in the calculations up to depth 3, what you can see is that log of pi appears in single MGFs, but when you put them together, log of pi disappears. We had something similar when we were working with modular graph forms and functions. In that big space, the expanded space of iterated integrals, the type of numbers that we had were mostly multiple modular values, which were like multiple zeta values or the L function of cos forms and things like this. But in the end, when we were going back to MGFs, all these L functions of the cos forms and all the I don't know, strange new periods, all of them were cancelled out. And we had multiple zeta values, and in some cases, the single valued version of multiple zeta values. But what happens here? Why this thing miraculously disappears in the calculations that we can actually do? And is it going to happen again or not? Especially because for something like this, so we like to have a good transcendental property of scattering amplitudes, but for something like this, we cannot assign a very good transcendental number. So this is a very big question that we should think of. And let me conclude by pointing out some connections to the resurgence techniques that we use in MGFs. So, for example, in generalized Eisenstein, a homogeneous term in the Laurent polynomial that you can add is tau 2 to 1 minus s with some coefficient, let's say mk s, something like this. So the way, one of the ways to determine this coefficient is to use the resurgence on the Q expansion of this Q and Q bar, expansion of this F, and knowing that this is divergent when you go to tau 2 equals 0, but these two together should be fine. But here in the integral business, you have yet another way to look at the same problem, which somehow doesn't use any resurgence or anything. And it comes from the fact that whenever we want to use this formula of the integral, so this is 0 to L, L to infinity, if the Poincare sum is divergent, this integral, these two integrals are also divergent. But with some good analytic continuation, these divergences get cancelled out. And this analytic continuation looks exactly like what you do in the resurgence of these Q bar terms of the function f. So instead of doing the resurgence on these things, one thing that you can do is to integrate something like this. So in order to do that, if you want to unfold this one, if you want to expand this one for the Poincare sum, you have to assume that L is bigger than m and k. And if it's not, then you analytically, no, sorry, okay. You have to assume that L is not S. This is also true, but this is what I want now. You have to assume that L is not S. And for the cases that L equals to S, you have to analytically continue this integral. So you have to first assume that L is bigger than S, analytically continue L to S. And you get the same coefficient, exactly this one that you got from resurgence. If you ask, all the divergences get cancelled out. So this is also in close relation with resurgence. Also, that's the reason that in the techniques that I were telling you, you don't see any non-zero Fourier coefficients anywhere. So all the integrals, the result of all the integrals in all techniques, it's independent of the non-zero coefficients because they have some kind of very strong secret connection somehow. Okay, I think it's a good place to stop. Uh, when tau 2 goes to 0. The Q expansion. Yes. Q bar expansion. Personally, I find the other way much easier. Because, yes, that's one of the reasons. And the other one is that you can immediately, using this, you can immediately connect this with the residue of the Rankin-Selberg. You can write a general formula for any of them. Nothing. Nothing. Even the new functions at depth 4 is not known. So the obstacle. So okay, let's say that we want to solve this easiest example. Then, in order to solve it, you have to solve this sum n1 and n2, and 1 to some power and 2 to some power. You have to calculate this, and this is not a Dirichlet sum, so you don't have near Ramanujan summation or anything to work with this. It comes from the Rankin-Selberg L function. Depth 4. Yeah, so it unfolds one of them, and then the rest of the sigmas are for this 3. And then you have to integrate, so the integration gives you these things. Yeah, actually, if you want to, that's the thing. So if you want to use, for example, the other formula, you see this also for depth 3. But there's a way to skip this, and it's using other techniques. Because, okay, it's not this that you get, it's a residue of this that you get. And without knowing this, in this specific example, you can get the residue without knowing it. But if you go higher, you have to know this. There's no other way. Well, one thing that I learned recently is that potentially numerically you can write it, but Usually these things are convergent, and numerical methods are not very good. Yes. Yeah, it also comes from another convergent thing that putting them together are analytical continuations. So Danziger said that these things cannot be calculated, so anyone else says the same after that. Yeah, I would really want to know some general arguments, anything above that, because for the sake of calculation, actually 6 and 7, alpha prime to 6 and 7 is already too high, so let's have some general things.